record on this computer. Okay, hi again. Let's resume about our discussion we had this morning. So in the morning sessions, we discussed using Flopy to construct simulation cases for model flow 6. We briefly discussed about the field conditions where we monitored water levels in the bores, the surface water level, and the surface is subjected to infiltration plus evapotranspiration, which causes the water level to draw down. And we briefly discussed about the domain, how we are going to set it up. We also mentioned that the surface elevation will be able to describe a bowl-shaped pond right in the middle, so that the recharge area is all dependent on the surface that is water inundated. So when the water depth is smaller, the area of the pond will decrease as well. So that is a function we need to implement. We briefly discussed that how we are going to simplify the recharge process. So it's a very simple Darcy's law where the hydraulic head, which is D, thickness of the pond, plus the length divided by the overall length times K, is the recharge rate. So by this assumption, what we assume is that the storativity in the unsaturated zone is negligible, and also the rise of the water table does not significantly affect the discharge length. So we can see whether this assumption works for our model or not. We're gonna give it a try. To be able to do that, we need to consider the bathymetry of the pond. We also need to allow the water depth changes in time and space. Then we briefly discussed about the monitor data where the surface water pond increases and decreases, which literally change the D here. And we use that as I found to calculate the recharge and use the rise of the water table for calibration. So if the model can sufficiently reproduce the rise of the water table as a result of recharge, we believe that this simple recharge model is able to work. We also talked about the stress period. So stress period is a way to lump a few time steps all together, during which the domain shares some similar boundary conditions such as recharge, evapotranspiration, or even constant heads. So if we have, so that once we apply the boundaries within the specific period, all the time step in that stress period will have the same boundary conditions applied. We also discussed about the three different types of cells within model flow. So this is a vertical 2D domain, and then here is the water table. So first is the top cell, that is where water level is below it. So the cell will be considered as inactivated. There is a big story about how to convert from dry cells to the wet cell that will be covered from our later tutorials. The second types of cells is the cell that is unconfined, which means that the water table is within the cell, and the hydraulic head of the cell is in between the lower elevation and higher elevation of basically the bottom and the ceilings of that cell. So that's the hydraulic range. And specific yield is the key factor that affects the rise and fall within. Finally, we got another cell where the water table is above it. So the cell is fully water saturated, but the cell itself will subjected to expansion and shrinking as well. The shrinking is more or less induced by the soil matrix compression, which is relatively small. How small it is, if you try to put in 0.1 millimeters of water, the hydraulic head within that cell will be increased by 1 meter. So that's just a kind of indications. So 3 different types of cells. No unsaturated zone within model flow. So if the cell is above water table, it's considered as a inactive cell. But we have UZF packaged, but that is a very specific conditions. And then we discussed about 2 different ways to interact with the Python code. So we provide a Python code, a PY code, where you can run the whole code by click this button. You could do debuggings by putting a red dots and then click the run, and then you can step or next to give you an interactive way to talk with it. You could also run a specific cell, let's say here cell 2 by control plus enter, and then you can interact with it. But the issue for Python code is that it doesn't really store the result that comes out from the model. So within GitHub, you probably only get your Python code, and over 10 years later, you even forget what type of outcome will be produced by this Python code. So we decided to use IPYNB notebook files to demonstrate that, because as you can see, some of the codes that's being carried out, the output is also on the screen and it's going to be stored there. So it gives more intuitive or the whole picture of the Python code. And later on, when you look at the graph, you know, oh, okay, so this is what the code is going to give it to me. Obviously, GitHub needs to take care of those outputs, but hopefully the size of the output wouldn't be too significant. So that's where we are. We've already covered a few cells. So commented cells, it's just an overview of the cell, of the project. We have import libraries, import Flopy, which is the library we use to create pre and post processes. Print out formats, initialization of plotting parameters, and create a dot dictionaries that is easy to lump all the properties all together. We also have the unit conversion parameters here, so that we never use 1000 to do the conversions. And the reason is because in 5 or 10 years later on, when you look at the code, you know exactly why you multiply some values by 1000. This is to change probably millimeters to meters to millimeters or whatever. A dictionary that shows all the sensitivity analysis, which we will discuss later on. So the size and dimensions of the cells, which we have finished. Now let's move to the next few sections. So this section 8 is to create the model and time discretizations object TDIS, so time discretization. So I called this model name as e-watering, and all the files will be stored at a folder called model. So we know that our current working directory, as showed in the output, is here, right? And then if you look at my screen, I'm having D drive project and e-watering. So that's here, right? So you will see that you've got a model folder, and that's all the input created by Flopy and outputs. So that's where it is. That is where it is. I always recommend everyone to use this command to use. This is not strictly correct, because if it's Linux, this is stash, but if it's Windows, it uses backslash to tell the differences. But anyway, so working directory is already been given. Now we are going to use a library from Flopy. So Flopy MF6, which indicates its library for model flow 6, and it's to create a simulation. So that's why it's called sim. Simulation name is model name, which is e-watering. The version of model flow we're going to use is MF6. The execution the execution file name is, well, originally was said exe MF6, and currently I'm not going to put it here. I actually have a model flow put in our environmental variables, so I don't give a specific name. So how that can be done? So I'll show you that in my computer, you can find out my PC. So if you open your my PC properties, and you will be able to see a advanced system settings, right? Then in the advanced system settings, you have the environmental variables. And within the environmental variable, there is one thing called path. So basically the path is the location where the computer will look for execution of files. So for my particular case, my files are stored in CMINGW-BIN. So that's where it is located. So if I go here, MinGW and BIN, and you will see a model flow 6, MF6. So that's where this model flow execution of file is located. So if you have your mf6.exe, I would recommend you to store into a system pathway. So every time you run the code, they are able to find it. So then how to compile it? You probably can go to PyMake, which is the so far the best place that I compile the code. So if you go PyMake, GitHub, so you again git clone the whole package, and then you can do the examples, and you can make, you just use Python, make MF2000, and that will be ready for you. So it's that simple. I always use this way to get my execution of file, because model flow is totally free and open source. So that's very, very handy. So now I move back to my working directory. So that's basically talking about where you need to store your mf6.exe file so that it's able to be executed. Now, I'm trying to put it as detailed as possible so that you could always come back and then create your directory. And the SIMWS is the working directory, which is in the model, right? So you probably will have a question. How did I find this command from Flopy, right? Yeah. So the answer to this is that always go to examples. So we have the model Flopy, that library, and then we have Flopy. And you go for, let's say, examples. And then you could go for, let's say, tutorials. And then you have model flow 6 tutorial, and then they have this tutorial here. And then they also use the same command, right? So Flopy MF6 MF simulations, right? So always try to use examples to get where how other people is doing this, and then you copy and paste. The other thing that I normally do is that I go to Flopy here, and then just search. I search that whole thing. And then you will see that it has a few Jupyter notebooks that use that command, and you just copy and paste. And there are so many examples. So Flopy is a very good location, which has many examples. The second place I would call is model flow 6, GitHub. They have another one called model flow 6 example. So that's the two main places that I do my search. And if I need a lake package, I'll probably find out the lake package from any of the examples, and then I copy and paste. So essentially, for use codings to get your simulation work, the most important thing is to just try to get some of the useful code from the well-established projects. And if you have got 5+ projects that you run previously, you've already created your own libraries. So that's the way how we manage to get our own projects. Now, just go a bit further. So now we create an empty DIS periodical data, and this array here basically tells that this is an array. And within the array, what I did is that I create a kind of DIS periodical data array. So if you would like to see the size, what you can do is that you get a console, right? And then you can run it here. So what's this unit look like? This array looks like is that it first has the simulation, T simulation, which is the length of each stress period. The second is the number of time steps within the stress period. The third is T multi. So if it's average, then it's 1. So that actually, so in total, it loops through the number of stress period. So basically every single element here is for 1 stress period. So for that particular stress period, it is 1 day, and within the 1 day, there's only 1 time step. And then the 1 time step is averagely distributed. So literally we have 360. So NPER is, I think it's 350, is 350. 350 stress periods. Each stress period has 1 time step. If you want to have more time steps, you just need to change the NTSP from 1 to the number that you would like, so that it becomes that you have still 350 stress period, but within each stress period, you actually have got 2 time steps. So the total time steps for the model is 700. That is to refine your discretizations. So one of the things also, some of the model user being familiar is that they don't really use Kural number to back calculate the most suitable time steps, which TUF is using. This has been here for a while, and I believe this would be the best way to arrange time step by now for using model flow. So now we've got this array ready, and then we can move a bit further. So Flopy MF6 model flow TDIS. So this is time discretization. And this time discretization is served for the SIM, which is this model. And the time units is going to be days. So this is very important. So now all the time unit is going to be days within the model. And by specifying this, the number of stress period is 350 as according to MPER. Then the periodical data, which has this, is included into this tiny object. So after run this, the time discretization of the model is well defined. So this is also something, why we call it model flow. So it's very modularized. So this tiny functions is basically a time discretization package. And if you set up this object, you would have a file that is called TDIS there, which is only to store all the inputs for time discretization, and the space discretization is being stored in another separated file, which is also an input. Let's say we probably have a TDIS somewhere. If it's not TDIS, then it might have another name. So I'm not sure. Oh, okay, so this is TDIS. And if you open it up, you will see that it's the number of stress period and also the array that is being stored here, which is exactly the same as what we specified here. But remember that this was created in the morning when I run the whole thing. So currently, even I run this code, run this particular code, it hasn't been written to the file. It's only the file that was executed not last time, right? So that's about time discretizations. Now we need to talk about what type of simulation we're going to run. So we would like to do a groundwater flow. So that's the GWF here. This one serves for the model SIM. So the model name is called flow model. And then the Newton options is true. So this one, I believe it's related to the way how the linear system is going to be solved. So I copied it, and so far I don't know what does that mean. So if we really want to know what does this mean, you can copy the whole command and Google it, and it will come with a Flopy read docs IO. And in here, you probably can get Newton options, right? So if I just search this particular option here, so basically says that whether the groundwater head in the cell will be relaxed when water level fall below the bottom of the model in a given cell. Okay, so you see that Newton-Raphson under relaxation is not applied, which means that by default, it's not being used. Anyway, so usually if the model is not converged, that's the moment for us to consider about these parameters. But for now, as long as you get the result, you don't really have to retune the convergent criteria. So the next section, section 10, is about how are we going to solve the linear systems. So it has the outer iteration and inter iterations. If you are a old modeler, you understand that inner iterations is the iteration to solve the linear system using a sort of conjugate gradient methods rather than Gaussian de-animation method, which is very time consuming. The outer simulation, the outer loops are all for solving a nonlinear system. So you do the guess for permeability, transmissivity. So it's very similar for all the numerical models. So I basically copy and paste the whole thing. As said, when the model does not converge, even the input looks perfectly okay. That's the moment for us to tune these parameters. Next is about the input conditions. Remember that we discussed in our slides that the surface water depth measured from the field will be considered as input because that will tell how much water is being recharged to the water table. But there's a problem. This particular, the measurement is measured from the field at the interval of, let's say, 1 hour. And always the 1 hour is not accurately 1 hour. It's probably 8:35, 9:35, 10:35. Now, if we create our model, we want to just get 12 o'clock every day, 12 o'clock every day, because the time step is 1 day. You will see that this discrete data does not give you the head at that point. So what we need to do, we need to do an interpolation. So you have a few points and then you find out at that specific time what is roughly the head. So the way how we do it is to use spline interpolations, right? So that's why we call csaps. That's the function for spline interpolation. I'll create a dictionary called field. And then within the field, I create a variable which is explained by itself. That's simulation start time. And it has a format of DT64. And this simulation starting time is basically NP date time 2021 March 18th at 8 p.m. right? If you want to see how it looks like, you probably can copy and then paste it in here and then shift enter. So that's basically this point. And then I'll explain later on why we need to define this. But from now, we basically need to be able to obtain the CSV file. So I tell the system that this CSV file is located here. So this is something I would like to suggest everybody to use. So we know that the model WS is the location of data, right? And then we want to access this particular file. And to be able to add that folder in here, I always use OS path join, because if I do so, you will see it strictly follow the folder using the separator that is compatible to the operating system. So currently I'm using Windows, and then in Windows, the parent folders, the folders path is being described by this backslash, whereas in Linux it's actually a slash. So if you use OS path join, that basically allows your code to be compatible in both Linux systems and Windows systems. So basically, this is where the location of the PondDeps SA2, which is a CSV file. So I probably can open it up for you so you will see the format. So data and SA2. So that's where the file is. I can use a notepad to open it up, right? So it has TS values. So the first few things are time. The time is quite in detail, so even seconds. So you see the data is basically random. And then the issue, as you know, that we need to specify a water depth at each stress period, only each stress period, so 1 day per data. So how are we able to interpolate that? And you see the data originally starting from 0 and later on started increasing, right? And again, the other thing is that you probably, once you set up your model, you started with 1 day, and later on you realize that 1 day is very coarse, and you want to further refine your time steps. Are you able to, I'm pretty sure that you can manually get your data from by average every day, but how about per hour? And then you have to, if you use Excel, you basically have to redo this whole processes to make your code running like a whim. So that's why interpolation is very useful. So if you further refine your data, let's say in seconds, you don't really need to tune too much. So I'll show you how later on how it works. So that's the location. And then I basically tell read CSV. Now we create a new object called PD. So PD is in short for pandas, which is a panel data. So what it reads is basically the file locations as specified here. I would like to parse dates. So parse dates means that when you read it, there are two headers. One is called TS, the other one is value. So this is a panel data, which is like a matrix. But some of the matrix could be missing, such as these ones. But for the first column, it's been called TS. The second column will be called as value. Now, once this one is being read, the rows is not noted by 1, 2, 3. It's actually noted by TS, which is the date parse. And the index column, sorry, this is actually wrong. So this means that trying to get the dates to date num rather than a string. So you basically recognize what date it is, and you can do plus and minus here. But for this panel data, the index column is going to be 0. So that means that, for Excel, for example, we know the row indices are 1, 2, 3, 4, 5. But for this panel data, it's not 1, 2, 3, 4, 5. It's actually the time. So if I run this, you can see what it does. So you can see that in my pandas, is there a 1, 2, 3, 4, 5 for the rows? No, not really. The indices is actually the time, and also the time can do multiply to plus and minus, which means it's being parsed. The system knows that this is a time. This is not a string like my name. So they understand that. And also, once it comes to value, you see some empty values here. It's called not a number, right? So, well, what if we don't do the index column? So if I hatch this line and then rerun the code, you will see that, so is the execution completed? Yes, it's completed. Now, just try to see the difference. If I don't consider my TS, the index to 1, so when I hatch this line and rerun the code, you will see I have 1, 2, 3, 4, 5 as the index of my panel data. Well, you probably are familiar with 1, 2, 3, 4, 5 as locations. But in fact, using time as your indices is much easier because later on, we probably can get the average, maximum, and minimum per day, per hour, and that would be so easy. And also, if you want to get the data from one day to the other days, you just need to specify the dates, and then the system will understand. That's why, try to change a mind that for the row indices, use time rather than 1, 2, 3, 4, 5. And later on, you will enjoy it. And the other thing for the parsing dates, if I hatch this, you will see that for the TS here, it will be considered as a string. Well, so let's say for now, it's being considered as a date. So if I call this, and let's call maybe, number 0. Well, I need to actually use .loc. That's basically the first row. So you will see this, and then I can also access what they call TS. Yeah. So that's a particular time. You will see it's called timestamp. So they understand this string is a time rather than just a string. Instead, if I basically get rid of this, right? And then if I don't parse dates, well, I'm just saying here. So if I don't parse the dates, what you will see is that the TS will be considered oh, well, it doesn't really have a TS. Okay, sorry, I can't have these. Okay, let's open this one first, have a look. Okay, so what does this one say? So you got TS, which is your index. So an index, can I do that? Which is the first one? Yeah, so see, is this a string? This is not a string. And then if I do these minus that, I can't do that because it's string and string. You can't do subtractions in between the two. Whereas if I parse the dates, okay, so I'm basically go back to what I used to do. And then run the code by Shift and Enter. Now, if I run all the previous code by using upper and then do that, you see that it has a kind of time delta there. So it basically tells the differences. So that means it's being properly parsed, right? So that's basically our advantage when we store the data. Okay, so it's a long lines, but I try to explain this. So that's basically to read the CSV files into the system, right? Now, the second thing we need to do is basically unify the dates. So I basically say time elapsed days. So remember that we define a time when the simulation was started, right? So these are all the data from the panel, which is a column, the time, minus the starting time, which is the time difference from a specific time when we do the measurement to the time when the simulation starts. So if it's 1 year, then that number is 356. And then I divide that by a time delta by D, because if we subtract 2 times, it basically becomes a time delta, delta time. And if I divide that delta time by days, I'm able to get an array that tells what's the time from now, from the measurements to the moment when the simulation starts. Because once we do simulations, we need to say which day is the starting of the simulation. And then I can basically get 350 days, right? So if we look at the result, then you get the idea. So you can see that all the days, well, some of them is actually before the simulation because nothing was happening, no plant, so I don't really have to simulate that. But then it's the zero. The zero actually means water start of pumping, so the water level rises. And we also have the data up to 353 days since the beginning of the simulation. So that's basically my input. But again, my data is much more defined than I do. And also the timing is very, very different. We need to unify that, right? So that's the next thing that we need to do. So basically the whole process is repeated 4 times by getting, water table at SA2. Well, just go back to this, to the screen here. So SA2 is right in the middle, right in the middle, also shown by the blue point. SA3 is here. So go back here. So SA3 is at this point here, right? And then SA4, which is outside. SA4, which is here, and SA1, another point here. So basically now all the CSV files has already been in the system, but the timeline is much more fine than my specific time discretization, which is day 0, day 1, day 2, 3, 3, day 4, right? So we need to do the processes. How are we going to do the processes? Before we do so, we basically plot it out. So we create a subplots, 2 columns, 1 row, shear X force. So shear X force means that if this is true, when you change X limit, all of the X limit will be changed because they are identical. Figure sizes, constraint layout, true. And then I create a raw field data and font size as a overall subtitle. And then I'm going to draw on the first panel data. So in this first panel data, you can see this is very self-explanation. So it's the field data. The first is the pond depth measured at SA2. The DF is basically the panel data. The index, remember the index is time. And then I'll show the values, which is basically the word depth. And it will be shown as blue circles. The label is SA2 water table. The X label for that one is time. The Y is the pressure head, meters. I'll show the grade, and also the legend is upper right. That's what it says. Now we also do that for the second plot, but the second plot has got all the borehole data. So if I run it by shift and enter, you will see the result just appeared at here. So these x-axis are all time. So I'm basically trying to reduce the size a little bit. Okay. And that's been discussed previously. So rise because of pumping, draw down because of infiltration and evaporation, pumping again, draw down, surface gets completely depleted, rise again and draw down. And if it's rising, groundwater table rise almost immediately, which is due to recharge, but it draws down very quickly as well because recharge is reduced and also water dissipated to the all direction. Get another top up, rise a little bit and falling down to the original value. And then it rises again because we top it up again. So that's just the raw data. And again, this data has very, very fine intervals and uneven intervals as well. Whereas my model will require 1 data per day, right? So that's what we try to achieve. Now, so to be able to start with this, I need to get rid of some of the data. What data needs to get rid of? See, these tiny pumping events. So once we get water samples from the bowl, and the ball is emptied, and the pressure transducer will give us reduced value. And later on, we put the transducer back and water gets refilled to the borehole and it rises up. The good thing is that you can make use of that increase to back calculate the hydraulic conductivity of the aquifer. But this is not something I'm going to discuss today. Well, when you try to do the fittings, you don't want to look at these processes. So what you could do, you can get rid of this piece of data. So how to do it? Remember we discussed that once you want to do an interactive plot, you can use a code that starts with run get Python, this type of thing. Yeah. So if I run this code, right, shift the enter, and then run the whole command again, what you will see is that it doesn't give the result here. It's actually popped out, right? And now we need to look at where these tiny little things are, right? So I can zoom in, very tiny, okay? So you will see it's falling down and rise it up. I can basically shift around. So that case was taking place around, so it's just above my head. It's May 25th, and it's basically coming back around, let's say, early June. And those data, again, is basically manual processes. It's not going to be going through the interpolation. You don't want your interpolated result going all the way down and back. You probably just give a constant value there because the impact to the overall hydrology is very small. So you get rid of it. So how you can get rid of, we already know it's around May of 25th to early June. Yeah. So we just say that the starting time, DT is 64, so that's very important. We need to parse it. Is May of 25th, and it's finished in early June. Now, if you see how I'm able to identify the rows, I basically just use time start to time end. That's it. I don't care how many cells, how many rows are there. As long as I use this, it basically specifies that within this region, I'm basically highlighting this is the range of the regions. All the values is going to a NP or not a number, right? So in that case, if I run this command again and plot it, you wouldn't be able to see the hatch line. So this was before, right? So I go back to these. And what I can do is that I rerun this. I run this. Control shift control enter. It's executed, and then I plot it again using the previous cell. And you will see that this is missing, right? So it's not there anymore, and this is original. And these are actually the processed data that you need to do the interpolation. So if I zoom in, you will see there is basically a gap. But that doesn't really matter. You can always stitch the data, which means that, you know, the pumping events doesn't really taking place at all. And that's actually the data you try to do the interpolations. Right, so the next is to do, let's see, what is the next? So next is to create a simulation time array, which is on DT64. So, so I basically create a simulation time array. So remember that we have our own time. That's the starting point. And then this is basically the total IM that this is basically, you know, the key time points in my time axes. So remember, it's 0 to 350, right? So I basically create a time array that starts with the simulation time, and the interval is only 1 day, remember, right? So I can try to explain what really happens here by run this code. So if you run this code, it doesn't execute. So it should give me some result instead. Okay, so if I run this code again, and I want to show this. Okay, so now it's shown. So remember that my first date is 19th of March at, sorry, 18th of March at 8 p.m. Now you see that, you know, the interval between the two is only 1 day. So that basically aligns well with the data I need to as the input. So that's the time array that we used. And then based on that, I create a panel data. But, you know, the panel data only has got the indices. And then I can do the elapsed days, which go back to the 1 to 350, which is the time. This is basically my time array, yeah, the time array. And now I'm going to do the interpolations. So for my interpolation, I use this command. So the command has got the candidate for input, so that's the time axes. And the second is the water table. So the dimension of these two are the same. So this is X and Y. And this is my target. This is my target, which is the time elapsed days. And that has an interval of 1 day. And this has a very ununiform time axes. So after run this command, one of the things that we need to do is basically get rid of all the not a number, because this command does not like a not number. So I use this command here to basically get rid of all the lines. So it's a mask. Well, how to explain a mask? A mask is basically like a mask you put on your face, and then you want to only show the eyes, so that once you put the mask on, all the not a number is being hatched. So you can see it's basically true and false and these values. Yeah, so false and true and this type of things. And then I'll be able to get a water table SA2. So these is only the file, only the height at the desired time, which is defined here. And I also plot the figures. So if we show the figure, you'll be able to see that you can make a comparison between the two. So the red line is the original data, which is very fine, whereas the cross are basically interpolated results. So you see, you know, at the it's basically a time space of 1 day. So then we can use this data as the input. And if you want to refine it, you just need to define another refined time axes, and then that is able to do the interpolations for you as well. So you see that overall, this interpolation follows the pattern that is given from the field conditions. And then you can do the inputs. You can do the input for the model. So that's for the interpolations. Well, we also did that for all the boreholes, but that's not really necessary because the borehole is just for comparison. So what we usually do, as shown, I probably need to check my batteries to see I'm having enough batteries. So I need to put my battery on. Yeah, power battery on. So I repeated that processes to interpolate my SA3, SA2, and SA1. But in general, that's not really necessary because when we plot the result here, the final result comparison, we probably just see the overall pattern and we don't really care about their X intervals there. It's not really necessary, but I just put it in here for your reference. And it also plotted out separately, so I can jump quite a few lines. So it's doing exactly the same thing. Now, we need to move to the pond. So that's basically where the input is going to be used. So all the red dots, and that aligns well with our time steps. So we are able to get that. So it's literally the same way. Okay, now we need to look at our discretizations. First of all, I need to define a domain called I domain. So the I domain is a very important parameter here. So it has a few purposes. So for each cell, it has an I domain. And if the cell has a number greater than 0, it means that the cell is active, which means that the model will give you the hydraulic hits. If the I domain is at 0, that means this cell is inactive. Inactive actually means that it's not part of the calculation, so you can ignore it. So that is very useful when you want to get a circular domain. So if you do a circular domain, you probably still have to make a square, but for all the corners, you can cut it off and by using those I domains equal to 0. And I domain, if I domain is equal to -1, that actually means that the cell is conductive. So this is very important when at one location you have got 3 different types of soil, whereas on the other location, it only got the other location, the vertical stratigraphy, it only has 2 types. And that really means that the middle layers is not a cell at all. So you can use -1 to get rid of that. But for this application, that's not important. Everything is 1. So then we need to look at the space discretization as indicated by the DIS here. So it serves for groundwater flow model. Number of layers, which is 1, number of rows, number of columns for each delta row. So delta row meters, delta column meters. The top surface is currently it's only a fixed value, so it's 0. But later on, we need to put the surface that considers the kind of pan-shaped basin. And the bottom is basically the vertices for the bottom layer. So if we do that, it's basically -10 for the whole domain. And I domain is equal to 1. So it's temporarily prescribed. And so the next is to identify those special regions. So we've got several special regions. First is the circle. We need to define the circle. The second is basically the boundaries as indicated by the blue. So those locations need to be identified and the special boundaries need to be implemented into that region. So I used a function called gridgen. So I called it, well, gridgen, how I find this, again, search the example cases. So I find this and I put it in here so that if I don't really understand what I did before, I can go back to the example case and see, oh, okay, they managed to do that in this way. And then I decided to do the same thing. So when we run the gridgen, we need to basically get all the locations ready for it. And it also print out the gridgen locations. Okay, so first we need to design, the next cell is about find out the circles right in the middle. Given that it's a circle, so it has an origin. So this origin is being defined by Lx is the overall range 300 divided by 2, which is 150, and with 150. So the center. So if I can just run this to give you a rough idea what happened here. So so basically the center of X and Y is 150 and 150, which is right in the middle, right in the middle. And the radius of that circle is 100, as shown here. So that's 100. Now, to be able to identify all the cells that is enclosed by the circle, we need to define the perimeter of the circle. And to be able to do that, I create an empty array that is called circle perimeter. Circle, the perimeter of the circle, and in each sub list, it has X and Y, and it's an array. So how I managed to do that? First thing is that I need to tell that within that parameter, how many points I need to get. So I basically said 30. And then you see, this is MP range. And then it's starting from 0 to 2 pi, which is basically a whole circle. Yeah. And then pi divided by the number of points. So basically this is 60 points, right? Because if this is 180 divided by 30, which means that in each cell, it just increased by 60 degree. And then for each circle, I basically add the parameter X and Y by simple arithmetic trigonometric equations. So center plus the radius times cosine, which is Y, and then center plus radius times sine I, which I basically is the range. So that basically draw a lot of points, which delineates the circle. And how many points do you need? Well, you can put 100, but more or less you can draw a circle based on this, right? Now, when you finish this circle, the most important thing is that this array has to end it to a starting point and make a loop. So it's not a line, it's actually a loop, which means that the last point needs to be appended to, so the last cell will be exactly the same as the first. So if I go, so this is basically what I did here. So if I go to this circle, you check it, then you see that it starts from 250 and 150, 250, 150, to 250, 150. So that basically shows that this is a loop rather than a line. If it's a line, you wouldn't be able to enclose things. So that's basically to append the very last one. So I don't give the detail. I'm just showing you why I'm doing this. I can call gradient, I build it, I join this, and then that's basically the circles. Now I'm talking about lines, but we can go back with that later on. So circle parameter X, Y is the important thing. So remember, we define this closed line, and I just need to run this line. Say gradient intersect. This is all the looped circle, and it's a polygon. So basically, I show that this is a polygon, not a line. And I'll be able to get all the node number that is inside the circle. So if I get these and get the node number, and these are the node numbers where it's inside the circle. So that command is able to find that for you. Now, the second thing that I did is that I create a multiple lines. So 0, 0, x 0, then 0. So, and then the maximum x, maximum y, and maximum y, and 0. So what that means is that it's basically starting from here, go here, go here, go here, and go back to here, right? But this time I'm not going to try to get whatever it encloses. I'm trying to get what cell that this line intercepts, right? So the difference between the previous command and this command is that this is only lines. And again, I can use node number to show all the cells that intersect with these multiple lines, right? So I've already identified all the cells, and that is either being circled, enclosed by the circle, or that intercept the line. And this command is very handy. The reason is that if I want to increase my time and space, and this line are able to find out all the cells. So, well, this is not like kind of not hard coding. So I probably can use the first and end to be able to get that. And also I can handily pick some cells, but it becomes very clumsy when you want to change your delta X and delta Y. And this command, you don't really care about which cell is being identified. You just need to basically group them. So that's the advantage of this. Now, when we get to the node number, so my understanding for the node number is that it starts from here, and probably starting from the rows and later on to the length to the columns. But we need to get the layers, row, and column. So this line here is to interrupt them. So we talked about lines and polygons, right? So we basically find out the node numbers, then we also need to define the point SA3. So point SA3 at X is equal to 240.1. The Y is 150.1. So SA3 is somewhere at, so if we go over here, so 240 SA3, it's slightly different to what we get here. Let me have a look. So that's slightly different from what we got from the examples. So here is actually SA3, but if we want to change it to the Python code, we just need to change here. That's it. So we go back to this. Right, okay. So I again use the intersect, but this time the intersect is point. By the way, this 0 just means that which layer you are trying to get from. So given that currently our system has only one layer, this is 0. If you got multiple layers, you probably have to run the same command multiple times to identify the cells at different layers, because each cell has a unique node number. Now, when you get this point, when you get this node number, so I can get node number, I need to get the this is layer row column locations. Yeah, so if I run these, you will be able to see that this is the SA3 is at 0 layer, the 9th column, 9th row, and 16th column. And later on, we will be using it. We also will get the surface area of that cell. So this cell is 225, if I remember, because each cell has a length of 15 and height of width of 15 and length of 15, so 225. And why we need to get the surface area, because once we get the recharge from the output, it has a unit of meter cube per day. But usually when we look at recharge, we would like to look at meters per day. So that has to be divided by the surface area, which we will explain later on. So by doing this, we can also get SA2 locations and everything, SA4 locations. This is just a middle point here. And then I basically, print all the node numbers, which are not necessary, but it's just to indicate that the process are successful, right? And then I create a iDomain 1D list. And also I joined another working directories. So that is basically the interception methods that we used. Now we're talking about iDomains for recharge. So as we discussed for the iDomain, everything that is greater than 0 is going to be an active cell. But many times we could use iDomain numbers to identify the specific functionality of the cell. So probably if there's a lake that has a unit of 5, If it's a constant head, it's another different number. So for me, all the cells that is recharge cell will have I domain of 2. And if it's a constant head, which is basically the boundaries, which that will gives a I domain of 5, right? So it becomes relatively straightforward for me to do that because I have I domain. This is 1D list, right? 1D list means it's node number list. And then I can just identify all the node numbers there. And then I specify a I domain RCH. So this is more or less like a mask and giving a specific number. And then I could convert it back into layers, row and column, and it becomes my new I domains. And then I can basically put the I domains then back into the DIS I domain. So I revise that number. So remember at the very beginning, I only give a single value, but later on I revised it because the I domain is being updated when I got all the cells that needs to give a specific boundaries, right? So that's for the I domains. So discretization is completed. Now, the next one is about the initial conditions. So it's again another module. So the start head with a unit of meters is getting from these initial parameters, right? And then I need to create a layer row column matrix based on the start head. And I put that into the FIC object modules in model flow 6. So that's how the initial condition is being prescribed. Then we need to look at the flow conditions, right? So flow condition is being considered by the NPF packages. You probably, and most of the things here are basically copied from an example somewhere. But the most important thing for me is two things. Number one is the K and K33. So K is horizontal hydraulic conductivity with a unit of meter per day. And the day is being specified in the first place in the simulations. And the K33 is basically the vertical flow. And given that our system is homogeneous, these two values are the same. And so the I cell type is equal to 1. That actually means the transmissivity changes with the groundwater table. So what does that mean? So go back to this line. Remember, go back to the vertical discretizations. So transmissivity is a function of hydraulic conductivity times the distance from the bottom to the water table. So for this particular cell, the transmissivity is K times B, which is from here, where my cursor is, up to here. And these are subjected to change, and the model actually considered that. So I enable that so that if the cells is partially water inundated, the transmissivity will be changed. So that's the function that we implemented in the model. We discussed about the specific yield and specific storage, and the I convert from the menu shows that a cell could be changed from unconfined aquifer to an confined aquifer. So it changes the modes of the cells. Given that for our system, it's only one layer, so all the cells will be active. So this is not really necessary, but it will be necessary when we move from one cell to two cells. One layer to two layers. We also have the output controls. So we basically save the heads and we save the budgets. So this again is a copy and paste from examples. I don't want to go to the details. Now we need to basically consider the head packages. So first is that we have the stress period for the constant head. So the boundary constant head is always the start head. So it's a -6. So for these cells, what we need to get is a loop. The loop basically loops through all the node that intercept with the lines, which is literally these blue ones, yeah, these blue ones. Now, there's a little bit tricky that I need to say is that this node number, actually, once we run GridGen, some of the cells might be able to appear twice. And probably we don't need them twice. We only need them once. And to be able to do that, I basically use set as a set. So if you're, well, the general way is that if I have array 1, 2, 3, and 1, yeah, let's say A is equal to this, and then set A will only have one of the ones, see here. So, and that's what I find, that it actually has replicas. So we need to get rid of the replicas. And the system doesn't really like a cell that being prescribed twice, right? That's why it has a set. So the first thing that we get is basically the coordinate. Well, the coordinate is basically the layer indices, the row indices, and the column indices, right, of that particular cell. And then we need to specify that by layers, row, column, and the boundary of the constant head. So that's basically the start of the initial conditions. And we also need to specify a recharge to the system. So the this is not recharge, this is constant head. So we got 2 stress periods. Well, then we basically use this to specify the 2 stress period. So what will happen to the stress period 2, 3, 4, 5 up to 350? It basically carry over the number 1 here. So if number 2 is not being prescribed, then that just means it's the same as number 1. That's original condition. We probably are able to find out that input file if we are lucky. So I don't know what name it is, but probably it's called chd. So we can open it up and have a look. So the maximum bond is 76. So that's probably the total number. So layer, row, column, and then what is the initial condition? So for us, all is about -6. So stress period 3, 4, 5 up to 350, it's the same number. So I don't need to specify stress period 2. It's a redundant, but for now it's just kind of that something left by the model constructions. The other thing I also need to mention here is that so in model flow system, it actually starts from 1. Whereas in Python, it starts from 0. So sometimes Python has different layer, row, column indices as compared to what's being written there, but it's included already. But that's just an indication that once you try to look at the input files, you see that number is not consistent, and very likely it's because of the counting that Python starts from 0, whereas model flow based on Python starts from 1. Yeah. So that's the boundaries. So the boundary is being well prescribed. Then I need to specify. So the next one is to basically have a look. Okay, so the next cell is related to how we get a slopy, a pan-shaped, well, it's actually a cone-shaped like this, a cone-shaped bathymetry, right? So the way how I manage that is first, I define a pond bed slope, a tangent value of that, that's 0.03. So remember, in most of the slopes, we prescribe that as a tangent value, and that is around 3 degrees. I think it's, we probably can use this function to back calculate the degrees. It's actually, it's very mild degree there. Now, when we get the tangent value, and the next one, basically, we need to calculate the distance from the cell center to each of the cells that is inside the ponding areas, right? So which means, well, this is just a basic Pythagoras. So x distance, square of the x distance plus the square of y distance and the square root of the whole thing. So what this function here do is to, so basically for all the black cells, it calculates the distance from the origin to the middle of each cells, right? So that distance, that's what this model calculates. And then the maximum depth is calculated by the radius times tangent. So a way of showing this, well, I can easily draw a graph here. So if we just look at the cross section, so this is right in the middle, and then we have a slope, right? So the slope is basically this value here, and we have a tangent. So this value is equal to this over this, right? This is the radius of the circle. So we basically get the maximum depth of that, right? And then we are able to calculate the depth of the cell. And sometimes when we do this simple calculation, some of the cells will have a negative value, and then we, forcefully making it as 0. And then we are able to get a surface elevation cell, which has a indices of row and columns only, and then we use z-tops. So I guess that you probably can use a simple trigonometric geometries to be able to get this surface elevation, but it's just a simple geometry calculations there. Then I'm able to copy and paste some codes to be able to draw this. So the maximum thickness, the maximum depth is 0.25, which is very similar to the actual survey we did to the field. And then it's a circle areas. So that surface elevation is being prescribed, and then I basically replace the DIS top into this cell array. Yeah, so that's how the surface is being prescribed. Now the next stage is to look at recharge. Yeah, and so point SA2 that we need to basically get the point SA2 surface elevation. So we've got the surface elevation array in row and column indices. So we get the row of the point SAC, column of the point SA2, and then we are able to get the surface elevation of SA2 there. And I assuming that the depth of unsaturated zone is 5 meters. And the clay layer has a hydraulic conductivity from the big parameter groups. And then I'll be able to get the non-repeating node numbers for the domain in here. So remember, gradient intersect is obtained by gradient, and then I basically create another node number, but this one does not. It's a set. It doesn't really have any repetitions as indicated by the variable here. So I'm using a again, I'm not going to go to the details for these trigonometric processes, but if you draw a simple sketch, you get the idea how I'm able to calculate the surface depth. So in general, if I go back to the simple graph draw here, so this is the center of the pond, this is the boundary of the circle, which is, so this point represents here, this point represents here. So if the water depth, well, the water depth from the field is measured right in the middle. And if we are assuming the water depth here is this, that really means that for each cell at different locations, it has different water depths, right? If this water depth is positive, that is going to be the head applied for infiltration. Whereas if the depth is negative, that just means the cell is exposed to the air and there will be no recharge, so that the recharge rate is 0. So as you can see that if the water level goes down further, the recharge area becomes small and also the recharge rate becomes small as well. So that needs to be included. And the whole processes needs to be repeated by the stress period, by the cells as well. So the cutoff point is not 0, it's actually 0.01. So if the depth is less than that number, I forcefully make it as 0. So again, it's a very, very simple geometry calculations, but the idea is to ensure for all the cells that has a positive water depth or water depth greater than 1 centimeter, it will apply the pressure to the bottom. Whereas for the cells that are exposed to the air, there will be no recharge. And this is changing based on the water depth. That's in general the idea how we prescribe these layers. And then we need to have the stress period specified. So layer number, row number, column number, recharge rate, and then we create this recharge SPD. And then I put in the recharge SPD there as the input. So that's a very large matrix, and it has a name of RCH. So recharge is prescribed. Now we also need to get the heads from 3 points. Remember, we got 3 borehole points. We basically need to monitor the head change over time. So this is the observation package. So it observes for the groundwater flow. 10 digits will be used for calculating the outflow to store the outflows. We need to print out the observations. So the file is going to have a name of obs.csv. And within the CSV, it has head SA2, which is, this is basically the layer row column of SA2. And we want to get the heads. So that's basically the format. And we want to get that for SA3, SA4 as well. This process name is called OBS, and the input is going to be written at OBS file. So again, when we open up OBS file here, so it's probably here. No, this is actually okay, that's the recharge. That's the recharge OBS, but we have an OBS as well. So that's the OBS. Remember, there are only the SAs. So SA2, SA3, and SA4. So it has the row number, column number, lay number, row column, and row number and column numbers there. And once it's being produced, this CSV file will store the results. So we can open up the CSV file. You see, this is the time. This is the head at SA2, head at SA3, and head at SA4. Yeah. So that's what the result looks like. But that comes out when we execute the system. We also created another observation. This observation is affiliated to the recharge package. We want to basically export the recharge rate over time at 2 monitoring points. So that's why we would have RCH, which is recharge package, observation, and I need to initialize it. And the file will be stored as RCH observation file. That is the observation. 7 digits will be used to store the result. It is continuous measurements. And the file, the output file will be RCH, OBS, and CSV. It's again a CSV file. And within the CSV file, I need to get RCH at SA2 point, RCH at SA3 points, which are basically the area that is subjected to recharge. Remember that SA2 and SA3, they are all inside the domain, yeah? So I've got two types of observations. Probably, given we are already here, I can have a look at what the recharge files look like by open up this. You see time, recharge at SA2 and recharge at SA3. One of the things that I need to specify here clearly is that the recharge rate is an input, and we already know it before the calculation. So this is not obtained by solving the matrix. It's an input. But why I'm plotting this out? Plotting this out is just to check whether the input for recharge is correct or not. So it's a check. It's basically a check. So one of the check is that because SA3 is somewhere in a higher elevation than SA2, so when the water level is going down, the SA3 will stop recharge first, and SA2 will stop recharge second. And remember, when we look at the result that shows the recharge rate, you will see that for SA3, when the water level decreases, SA3 starts to have a recharge, but later on it becomes zero. That really means that the water table, the surface water level is just between SA2 and SA3, and later on even SA2 stop of recharge as well, which is induced by the surface water completely depleted. So that's a kind of indication. But again, this is not calculated by the model. It's actually a check of the input. Whereas the head at each cell, this is actually calculated by the linear systems. So that's for the monitoring packages. So you could make use of that for monitoring all the boundary condition you prescribed, which basically monitor one point over time. So the next one is the domain at the cross sections. So in general, when we look at the result, we tend to look at the aerial view, which is the bird's view. And sometimes we need to chop a cross section and see the results. So this one only just to show, the I domain setup. So for all the cells that has a constant head, it has I domain of 5. For the cells that is prescribed as recharge, it has a I domain of 3. Whereas the this point, 2 points, is active cells. It doesn't have any particular boundary conditions. So, using this type of visualization could tell how the domain is being determined or prescribed very easily. Because, when I use interception commands, I end up with a lot of node numbers. I don't know where are they. I don't know exactly where, where those cells are. But if you plot it out and then you see, oh, this highlighted area makes completely sense, that actually means your interception method works, right? So I domain is a perfect way of checking this. So there are some particular commands all from Flopy. You see Flopy plot cross section, and you just need to tell them that which row are you going to look at. And it also plot the arrays. This is I domain. So that's basically the cross-section area. And then we also have the one that I regularly show you, that it's these 3 points. So you will see again that the boundary cells being correctly identified, the locations of the balls are correctly founded, and also the circles has been identified well as well. So, it's very handy actually. So they can just use plot boundary RCH, plot boundary CHD. It doesn't have OBS, unfortunately, so that I have to basically plot that point there. And I plot the grids and plot XY ticks. So this plot map view, which means that it's a bird view of the domain. And then I get this graph. And once you prescribe your own model, you could just copy and paste your this code to construct your own code. And then I need to do the right simulation. So remember that when I run this command, it will write everything into the files, and then you can run the code. So if I run this again, you will be able to see that all the files has been revised. So currently the time is 10:54. So you see those files are already being revised to the new time. Right, so I just minimize it. Now, this is to run the simulation. And to be able to run the simulation, you really need to identify whether model flow 6 is in the folder. So currently in the bin folder, and I previously showed you where is the location that you need to save your model flow folder, and you need to add that into your environmental path. The other extremely important thing that I need to pinpoint is that before you run the simulation, it's always important to delete the simulation result obtained from previous runs. The reason we need to do that is that imagine your simulation, your setup doesn't work, and none of the head files should be produced because it's a parsing area. And then the model doesn't run. But once you calculate the post-processing, it still works. Why? Because the previous result was still there. So you probably will end up with a situation where the model doesn't run at all, but still you are doing the post-process, which is obtained from the last successful result, and then you get confused. So that's why you need to delete this file. And remember, we use try and except. The reason is that if the file is not there, don't stop running it. It's just to try whether they're delete it once it's there. If it's not there, don't worry about it. So HDS is the file that shows all the heads. So before we run that, this is relatively large. So this file has to be deleted. So if the model is not successful, we don't really have any HDS files there. So that's very, very important. So then we run the whole thing, and then it goes through 365 stress period, and each stress period has one time step that's been discussed previously. And then we get the whole results. Finally, we're moving to post-process. So for the post-process, the two big files that we need to look into is HDS and CBC. So HDS saves all the heads. CBC saves all the flows. So basically the flow from one cell to the other, it's all in the CBC files. And if I get the get times, so that is basically the list of time where there is an output data. So for these, you see for every single stress period or every single time step, we got a result. Yeah. So that's just a list of files that has the output. So I create a list here. So the list here shows that we want to show the result at the 11s, 101 day, 150 and 200 days. We need to get that result. Well, so it's kind of funny. So when we start off, pinpoint a date that we would like to see the result, there is a likelihood that that date is not there. Let's say I want to get a time at 11.5, but I don't really get that result because my output is from day 1, day 11, day 12, but there's no day 11.5. So what I did here is basically using ABS to show which time is closest to the time where I want to do a visualization. So that's basically the index of the total time outflow. So that identifies probably 11.11 the result. The result at 11th day is closest to the day 11.5. And then they basically show me the day 11th result. Does that make sense? So, so it's also a kind of exercise that we do to ensure the result can always run when we change the time steps, when we change the space steps. So, you don't have to do a lot of detailed programming. So, once you do the program, these details have already been considered. Then I can do the subplots. So it basically shows the rise of the water table. So these cross sections also show the tiny little pond on the surface. You see it's kind of going down, but as compared to the overall thickness of the aquifer is very, very small. And the rise of the water table is well, prescribed. So for this particular moment, when it's actually head at this of day 1. So that's actually the first day, very, very first day. That what is the rise of the water table there. I plotted the I-bond, I plotted the grid, and then I also have the titles. The next one here is basically to show the aerial view, and the plot, the contours and things. So, you can copy and paste the results. So that's the very last result that I showed here. And I basically copy and paste from another example. So, if you would like to show this result, you can copy and paste in the same way. The next is also a cross section. I don't have to go to the details, but if you want to use it, you can still copy and paste it. The next one is to basically get the, so the previous ones are all I kind of how the head distribute over space at a specific point. The other way to check the result is that you fix one point and you check how the value changes over time. And remember, these are being observed through those observation packages. So we basically monitor how the hydraulic head changes at the 3 boreholes. So those files is being created when we run model flow, and we would like to check the results. So before we do that, we need to read it. And the way of reading it is a very simple command. So it's numpy generate from txt files, and we basically show where the name is. And then in this, we've got time, we got hydraulic heads at this point. It's actually a time array, yeah. So that basically shows the domain, the dimension of that variable. And we also have the recharge. So it's time for the recharge at SA2 and the recharge at SA3. And that's basically the command to be able to get the result. And then we get a huge plot here. And what does this plot here do? So the first plot basically show what is the field data from SA2. And we also have the simulated data as well. And then the same thing applies for SA3. The same thing applies to SA1 and SA4. And this is the input for, this is the water depth in the pond, which is at the input of the model. And we briefly discussed about the recharge rate, which is the check whether the recharge function is being implemented properly. And remember, we discussed briefly that we want to show the result at these 4 days and plotted in different color. So that's overall how the result is being plotted. So you can always dig into the details to see how those data is being generated. I would like to show some of the very important thing that how I personally do the sensitivity analysis. So for this type of exercise, we actually have a very clear goal. The clear goal is that our model is able to somehow reasonably reproduce the data observed from the field, like these curves. But we have so many parameters here, right? And we probably need to say, okay, so this is a little bit lower, so we need to increase it. And this is probably a bit too high, we need to decrease it. And in many cases, if we run this for so many times, we probably forget where we did before, how much we have done before, something like this. And it will have a very systematic way to be able to store all the simulation runs so that you can always refer to what you have done before. And eventually, I mean, the best way is that you're not basically trying to run more new models. You probably can just look at all the previous runs to be able to identify what would be your next parameter sets. So this is the way that how I normally do. So I will first identify the key parameters and then write it as a string. So you see this string, basically it's a title string, and then I put it into a subtitle. And in here, what I have is what I have for at the very beginning of the model. So remember that what we did is this big dictionary. Yeah, so it has kh_san, which is 2, number of layers, and everything here. Yeah, right. So I basically put a title in this type of names in here, specify the variables that we put it in. The other thing I did is that I use this string as the file name that of this figure. So it's basically here, yeah. So it's file name save. And so if I run something and I go to the figure, I'll be able to find out that particular folder, sorry, the particular picture that stores the latest result. So if I just put into the details, you will be able to see. So same thing, but it has different IDs. Then what I normally do is that every time I run a code, the file will be generated automatically so that I can basically copy and paste the whole thing into a slide. And then I'll be able to compare this result very easily. Let's say when this is the first result, and probably this value is a bit too high, and I decided to decrease the specific yield. So, you know, I basically just compare, I click these two. So for these two, you will see the only difference is the specific yield. Yeah. And by changing the specific yield, you didn't really see the result has been affected too much. And then later on, I say, oh, probably the hydraulic conductivity of the clay needs to be decreased. And then, you know, as a result, you will see that recharge rate becomes reduced by that. So how I'm usually creating this type of small files that looks very consistent, it's very straightforward. So the way how I manage it is that I create a new slide. Yeah. I need to basically, let's say for this result, I want to basically reduce the hydraulic conductivity of the sand layer from 2 to 1. Yeah. And then I run the whole code by clicking this value button. And then it will run through. Yeah. So you see that it becomes empty. That means the whole system is starting up. And the way how for me to show whether the simulation is finished is to look at the busy here. So now it's very busy. And which means that it's not being finished yet. But you see that once I change it here, it will change the whole thing. And then it hasn't arrived yet. So once I got that, I'll be able to, now it's already here. It's the very last. It's becoming the very last one, yeah. So that's number 40, I guess. Yeah, okay, so that's done. So you see that if I slightly increase the hydraulic conductivity of the sand layers, the water table just, you know, bounced up. So I can go here and then just get everything by time. So you see the K sand is the newest data, and that was the previous one. So I'll copy. I basically copied that figure and pasted right in the middle. And I also copy the file name, Control C and Control Z. And then I highlighted here, in red. Red basically means it's decreasing. And the last run, what I had is this one. Yeah. So that was the previous attempt, and copy and paste. And then there's another thing which I didn't change. So I should have changed this case name into a, let's call BH. This case name is very important as well. Okay, so now if I just click this two, I can easily identify what will be the impact to the result when we change one values. So later on, if I have so many simulation runs, do I need to look back on this Python code? No, I basically look at this. And I usually, use some words to identify the differences. And if it's a good result, I tended to use a red point. So, when I browse through, oh, I see, oh, that result is pretty good. So that actually means, this is probably the best setup. And then you probably raise some questions that can also be highlighted. So one of the things, you could see that I will probably end up with hundreds of simulations, but still I can get lost very quickly. So how can we systematically manage all the simulation runs? My suggestion on this is that, so for this simulation, you probably find it's a milestone because some of the values are properly emulated, but you still have a new target and you don't know how to deal with it. And then you try to do another set of sensitivity analysis that you have been done previously. So then it's repeat and repeat, you still end up with hundreds of simulation results. So my advice on this is that probably, no matter how good your current results are, you always have a set of sensitivity analysis. So you don't really worry too much about how good the results are. You always do sensitivity analysis based on the previous instance rather than based on a better result. Because if you do sensitivity analysis for the better result, you still have to run the 100 simulations that you run previously for sensitivity analysis. And that makes your whole simulation to be 200. So it's always important to basically have a set of systematic analysis. And even later on, you got a relatively better result and you want to even improve better. And the most important thing to look at the sensitivity analysis is the systematic sensitivity analysis you did in the first place. So that's just overall the advice that I have for you to manage your simulation runs. To me, it saves a lot of time. And once I look at how the result is being affected by the parameters, I don't need to look into the Python code. It's the spreadsheet that has all the information, and probably can make use of that to see how I should look into different parameters and so on. So overall, it's about 2-hour tutorial to tell the details of how to use Flopy to create a model flow case that involves recharge and a constant head boundary. There are obviously many other things that we can look into, and that would be covered by our upcoming tutorials. I thank you very much for your time to go through these long tutorials. By the way, that I probably feel that I get COVID, so my throat is very sore, but I don't have any other symptoms. That's why I've been working at home. I believe that by this huge wave, we will more or less get it sooner or later. I hope you take care of yourself and your families very well, and good luck. Thanks.